See how Resonetics engineers nitinol for reliability using a melt process designed to optimize inclusion morphology and deliver stronger performance in high-cycle fatigue environments. It's a question of confidence. At nearly 40 million heartbeats per year, a nitinol heart valve frame needs to survive 400 to 700 million cycles over 10 to 20 years. The mitral annulus changes size and shape with every heartbeat. The nitinol frame is compressed slightly during systole, then springs back in diastole. Because the frame is affixed in multiple axes, these motions produce cyclic stress and strain. Every heartbeat causes microflexion of struts, strut intersections, anchoring feet or barbs, leaflet support regions, and atrial skirt attachment points, cumulatively resulting in tens to hundreds of fatigue-sensitive hotspots. The nitinol microstructure, and importantly its non-metallic inclusions, are critical to the fatigue resistance and the ability of the frame to maintain structural integrity. The process by which the nitinol is melted and its solidification kinetics determine the composition, size, and abundance of these non-metallic inclusions. Inclusions are intrinsic imperfections within the crystalline structure of nitinol. The size of these inclusions governs the magnitude of the stress concentration and thereby impacts the fatigue resistance of the structural form, a heart valve frame in our example. Raw material, nitinol production for valve frames rests in two camps, each producing a different nitinol microstructural matrix. Principally for medical devices, Resonetics uses a two-step melting process to produce a base nitinol ingot. Primary melting is performed with vacuum induction melting. Starting with nickel and titanium, the first step for Resonetics production methods is vacuum induction melting, or VIM, which homogeneously mixes the nickel and titanium. Through VIM, a preliminary homogeneous ingot is yielded, ready for the next step, vacuum arc melting, or VAR. In the VAR process, smaller VIM ingots are consolidated into a larger ingot by VAR. Essentially, the ingots produced through VIM become the electrode used in VAR, through which an electrical current is run, producing an arc that grounds to the bottom of the receiving crucible. Through this process, a consistent nitinol base metal is produced, primarily with small, evenly dispersed carbide inclusions. An alternative melting technique forgoes the initial VIM homogenization and instead uses vacuum arc melting throughout multiple cycles, also known as VIM-VAR or VAR-VAR melting. First, nickel and titanium shot is placed within a compression form. Then the shot is compressed into briquettes. The briquettes are then welded together to create an electrode. This process cannot produce an electrode without microscopic gaps between shot fragments. The next step in VAM-VAR is vacuum arc melting, VAM. As the arc melt proceeds, unmelted nickel or titanium shot often fall into the melt, compromising the homogeneity of the resulting microstructural matrix. An inhomogeneous microstructure is produced, requiring additional remelts, each of which produces predominantly oxide inclusions that are usually larger than carbide inclusions. Two processes yielding two distinct microstructures with two distinct inclusion profiles. The abundance and/or homogeneity of the inclusions governs the probability of where within the medical device will be subject to undesirable stress concentrations and therefore susceptible to premature fracture. Limited sampling can falsely indicate a pristine microstructural profile, but a thorough random sampling reveals a more realistic view. This closer look reveals large, structurally significant oxides, while in contrast, a full sampling of Resonetics nitinol reveals evenly dispersed carbides. It's a question of confidence. From melt to market, Resonetics is your partner.